Kia ora, year 11, 12 and 13. I've just realised that I haven't videoed the excellence questions from last year's integration paper, so I'm going to get those done tonight. The first one that I've chosen is a differential equation question about a candle. It's probably the most straightforward of last year's 3 excellence problems, and this is it here. So as usual, pause the video, have a really good go at the question first, and then watch me go through it. I'm going to go through this more slowly than I have been in some of the A-level videos, so some of you will find this a little bit too slow, others will find it maybe a wee bit too fast. If you're finding it too fast, go and use Education Perfect for the basic DE skills first. So we're given an equation, a differential equation, that looks at how the mass of a candle is changing. So the mass of the candle was M, T hours after it was first lit. And this gives me the rate of change for that candle's mass. And what we need to end up with here is an equation that looks like this, M equals blah, blah, blah. We're told that the initial mass of the candle was 140 grams, so that means when T is 0, M is 140. And 3 hours later, so when T is 3, the mass had halved, so M equals 70. So notice up here we're guided about using T as hours, not minutes. You could do the whole thing, though, with minutes, and it would still work out. You'd just get different constants. Now, this is good because we've got 2 facts here, and we should know from practice that usually when we solve a DE, we end up having 2 unknown constants that we have to work out. The only technique we've really got in calculus so far for solving differential equations is the one called separating the variables. And that's where I'm going to get all the stuff with M onto one side, like this, and all the other stuff to the other side. So here we get negative k dt. And we're going to integrate both sides with respect to M here and with respect to t here. So on the left-hand side, we have the natural log of M minus 10. And on the right-hand side, we have negative kt plus c. There are different ways to go here. You might want to substitute in t equals 0 now, but I'm not going to do that. I'm going to do e to both sides. I get m minus 10 is equal to e to the negative kt plus c. And I can rewrite this as e to the negative kt, e to the c, which is a e to the negative kt. Okay, so this is just an arbitrary constant. Again, if that's feeling difficult, you need to go and do some easier problems before you tackle this one. Now we've got m is equal to 10 plus a e to the negative kt. And you can see that we've got this equation for m, but we've got 2 things that we don't know yet. We don't know this will be some number, and this will be some other number. So the first fact that I'm going to use is that when t equals 0, m is equal to 140. So we're going to substitute that in. 140 equals 10 plus a e to the power of 0. That gives us a is equal to 140 minus 10, which is 130. So now our equations become this. M is equal to 10 plus 130 e to the negative kt. And we'll substitute in t equals 3 and m equals 70, right? After 3 hours, the mass has halved and it started at 140. So we get 70 equals 10 plus 130 e to the negative 3k. Now we have to solve for k. So 60 equals this. 6 over 13 is equal to e to the negative 3k. The natural log of 6 over 13 is equal to negative 3k, giving us k is equal to the log of 6 over 13. Now this thing here is going to be a negative number, divided by negative 3. So when I put all that together, I get k is equal to positive 0.2577. And now we've got a solution for my candle mass with no constants left in it and lots of lovely coefficients. And it looks like this. Okay, so if we look at this, it makes lots of sense, hopefully. If we were to graph that, what would it look like? Well, it would look something like this. Okay, this point here would be 10, and you can see that here we've got a negative power for the exponential, so it's a decay curve. Well, that's wrong, isn't it? Having a complete brain meltdown. Look, when t equals 0, we know that the mass is 140. What this is showing me here is that the candle is never going to go below 10 grams, and I'm guessing that's probably because that's the candle wick or something funny like that. Okay, so you don't need to draw that graph, but it's always good to try and visualize what's going on with the situation. But we haven't finished the question, not surprisingly, because so far it feels a little bit on the easy side for an excellence level 3. We have to figure out how long it will take for the mass of the candle to reduce to 50 grams. So we go back down to our equation, and this is the easiest bit in many ways. We're going to solve 50 equals 10 plus 130 e to the negative 0.2577t. So subtracting 10 gives us 40 equals 130 times that. Dividing through both sides by this gives me 4 over 13 equals this. Now I'm going to take logs of both sides. So it's a very similar process to what we did up above. Finally, we're going to divide through and get t is equal to this. Which gives us what? Now, I have confessed that I've actually just grabbed that number out of the schedule. I haven't done that on a calculator myself. I'm hoping that that's perfect. I don't like leaving it as 4.57 hours. I'd like to work out what that is in minutes. And to the nearest minute, that gives me 4 hours, 34 minutes. Okay, so there you go. There's lots of great DE questions in Delta, both the new Delta and the old Delta, and also on Education Perfect. One good place to start looking is the problems on Newton's law of cooling, which are a little bit like this one. Thanks for watching. I will do the other 2 questions in about half an hour's time.